All right, let's revisit PES or photoelectron spectroscopy before we move ahead. Remember that we can be given a PES, a photoelectron spectrum, and use that data to understand atomic structure, electron configuration, ionization energy, and other periodic trends. So some of those questions are going to be coming up here in this presentation, and so I thought now would be a good time to stop and review what PES is and how that data is gathered, how that data is presented, and what that data means. All right, so let's talk about how the measurement occurs in photoelectron spectroscopy, PES. PES measurements are done using a spectrometer, okay, and this is like a little inside of the spectrometer picture here. It uses high energy radiation of some specific energy, some given value. Here it's an X-ray source, so high energy X-ray with an energy equal to h nu or HF. Remember that's frequency HF, so that has some given energy. And that energy is fired at some sample enough to remove electrons. So remember that if you remove electrons, you form an ion. So this is where we say that the sample is ionized or electrons are removed from it, okay? So electrons in this sample are at various energy levels in subshells, right? And they require different amounts of energy to be removed. Electrons closer to the nucleus are harder to remove and would require larger energy. Outer electrons or valence electrons are easier to remove because they have weaker nuclear attraction, they're farther from the nucleus, and they would thus require less absorption of energy to be removed. Okay, so various electrons are removed, and then let's talk about what happens in here on the next slide. So remember that this is a very specific amount of energy fired at the sample. Any energy that's not absorbed by the electron in removing it from the atom, so any leftover energy after that absorption, determines how fast the electron is moving when it leaves the atom, when the atom is ionized. If only a small amount of energy is needed to remove the electron, say for an outer electron or a valence electron, a lot of energy is then quote unquote left over, and as these electrons enter the electron analyzer, they will be moving very fast. So you see how there's a variable velocity here. Those electrons will be moving very fast. If a large amount of energy is needed to remove an electron, so if we're talking about a more inner or core electron, not much energy is left over, and these electrons will then be moving very slowly. So the speed at which they enter this electron analyzer helps the computer read out the various energy levels, which is what you see on your PES spectrum that you read. All right, so here's what you might see presented to you in data. Along the y-axis, you'll have signal intensity, number of electrons, or relative number of electrons. These are all related. Along the x-axis, you have ionization energy, binding energy, or units of energy, megajoules per mole, or electron volts. Those are energy units, right? And the scale goes from a very large value, so very high energy, down to a very small energy, and often there can be big breaks in the scale that you will see in your PES data. Okay, so what features might we see on a PES of a multi-electron atom? So I've shown the example here of the PES of silicon, Si, and I'm showing the electron configuration here, 1s2, 2s2, 2p6, 3s2, 3p2. And here's what the spectrum looks like. It starts, we have 1,000 here, then 100, then there's a break to 10, 1, and 0.1 megajoules per mole. And on the y-axis, I have my number of electrons, okay? So a few things to point out. The higher the energy, so here this highest energy peak, those are electrons taken from the core levels or the inner electrons. So for this silicon, that corresponds to this 1s2. It's closer to the nucleus, and the stronger nuclear attraction makes it harder to remove, requiring more energy, okay? See also that these peaks are all, well, this peak is a different height than the other four. The height, or the area of the peak, relates to the number of electrons in each subshell. So this 2s2 peak height is 1/3 the height of this 2p6 peak. Do you see how this is 1, 2, 3 times as much? Because there's 3 times as many electrons. And then finally, the lower energy peak, these are the electrons in the valence shell, or those that are farther away from the nucleus. The presence of each peak corresponds to the electron configuration. Each type of electron, that means each subshell where electrons can reside, has a peak in the spectrum. So we just use the electron configuration 1s2, 2s2, 2p6, 3s2, and 3p2. Here are the PES for hydrogen and helium for us to compare. So you have hydrogen on the top with this peak and helium at the bottom with this peak. So for hydrogen, this is the single electron in hydrogen. It has a binding energy or ionization energy of 1.31 megajoules. The height of the peak here is related to that single one electron. In helium, the peak is bigger. The height of the peak is related to the 2 electrons, so it's twice as big. The binding energy or ionization energy here is 2.37 megajoules, requiring more energy to remove. So the 2.37 is greater than the 1.31. It requires more energy to remove those 2 electrons from helium because there are also 2 protons. There's a greater effective nuclear charge that requires more energy to remove the electrons. Here's a PES comparison of nitrogen on the left and oxygen on the right. I've written the electron configurations so we can see the difference. We have 1s2, 2s2, 2p3 for nitrogen, and 1s2, 2s2, 2p4 for oxygen. So oxygen is 1 element to the right on the periodic table. So again, we go from high energy to low. The higher energy peak will be as a result of the inner electron. So in this case, the 1s electron. So this peak right here is the 1s electrons at 39.6 electron volts or megajoules per mole. Here it's 52.6. Okay. The 2s electrons are next, 2.45 for these 2s electrons. And in oxygen, it's a little higher, 3.04. Why is it a little bit higher? Well, again, oxygen has an additional proton in the nucleus. So those 2s electrons are experiencing a greater nuclear charge, okay? And so that means it will require more energy to overcome that effective nuclear charge and remove those electrons. And the last peak, this last peak is due to the valence electron. So 2p3 for nitrogen, energy of 1.4. 2p4 for oxygen, energy of 1.31. That's interesting, right? For nitrogen, it's a little bit higher, very slight, but slightly higher. Why? Well, this is a half full p subshell. Okay, so there's increased stability there. Increased stability of the half-full 2p subshell, which requires higher energy to remove the 2p3 electrons than the 2p4 electrons in oxygen. Okay, so subtle differences here, right? We still see a peak for each of the same subshells in both elements, but slightly different values. And then also notice this peak is a little higher because it has 4 electrons versus 3.
Another thing you can determine from a PES is ionization energy data. Remember that a PES looks at the energy required to remove electrons from an atom, and that each orbital appears as a peak on the spectrum. So we have lithium and beryllium here. For both lithium and beryllium, we have a peak that's the same relative size for the 1s2 electrons, and the energy here goes from larger to smaller. So this is at a higher energy than the second peak, which is for the 2s electrons. So we have 2s1 for lithium, 2s2 for beryllium. So we can clearly see here that the energy required to move the outer electrons for beryllium is much higher than the removal of that one valence electron for lithium. So beryllium has a higher first ionization energy than lithium, and that's because beryllium has the higher effective nuclear charge. More protons in that nucleus hold those electrons in tighter, or it requires more energy to remove them. All right, let's look at one last example of some spectra and answer some questions before we do some multiple choice. So we have this spectra for hydrogen, helium, and lithium shown. And I'm going to make them a little bit larger so that we can look at the values. And I'll just scroll a little bit to the question so you can see. But for hydrogen, we can see that we have one peak here at 1.31. And let me just circle it. And there's a 1 above it, and that 1 stands for the 1 electron in the 1s subshell. All right. And then the second spectrum that we see is for helium, and we can see that there's a single peak at 2.37, and there's a 2 above it, and that 2 represents the 2 electrons in the 1s2 subshell. All right, then lithium, we see there are 2 peaks. There's one peak here at a very low energy, 0.52, that has 1 electron in it, and then a second peak here that has a much higher energy, 6.26, and it has 2 electrons in it. And we know the electron configuration for lithium is 1s2, 2s1. Okay, so let's go to the questions and see if we can't answer them. Number 1, why is the binding energy of the electrons greater than He in helium than hydrogen? So look at the values for He. The binding energy is 2.37. For hydrogen, it's 1.31. The peak corresponds to the same 1s subshell, but the energy is greater. Why is the energy greater? Well, because helium has an extra proton, right? So helium has a greater effective nuclear charge, right? More protons in that nucleus, and you're adding electrons to the same orbital. So the shielding is the same. There's no shielding here. And those electrons then are held more tightly. Okay, and so that increases the energy. Okay. Number 2, again, I'm going to scroll just so we can continue to see our diagrams. Number 2 says, which peak in the lithium spectra represents the valence electrons? So valence electrons are the outermost electrons. So if we take a look at the electron configuration that we wrote, the outer electrons is this 2s electron here. And it's only one electron. And so the peak for that one electron is right here. Okay, so the valence electrons have a lower energy because it takes less energy to remove the outer electrons than it does the inner electrons. So the lithium peak is the 0.52 peak, okay, with one electron. Number 3, why is the valence peak binding energy less in lithium than in hydrogen? So it's asking us to compare. Why is this outer electron energy 0.52 less than this outer energy, binding energy for the outer electron so much greater at 1.31? Okay, so why would we expect that? Why would we expect to see a higher energy for the hydrogen than the lithium outer electron? Well, lithium has these inner shielding electrons, right? So lithium, the shielding is increased in lithium, which decreases the force, right? The force, and therefore also the energy. Okay. Then finally, number 4, why is the core peak 1s binding energy greater in lithium than in hydrogen? So for hydrogen, the 1s peak is here at 6.26, and for hydrogen it's 1.31. Why is that 6.26 so much greater? Well, again, we have increased effective nuclear charge, right? We have 3 protons in this lithium nucleus. So we have more protons, more effective nuclear charge, and therefore increased energy. Okay. I'm going to pull the answer tab. Let me make this smaller again. And I'll pull this tab. So, number 1, why is the binding energy of the electrons greater in helium than hydrogen? Similar shielding, but greater Z. 2, which peak in the lithium spectra represents the valence electron? So we wrote 0.52, and that would be the one with the lower binding energy. Number 3, why is the valence peak binding energy less in lithium than in hydrogen? Increased shielding due to core 1s electrons lessens the Coulombic force. So that's what we wrote, okay? Increased shielding, decreased force. Number 4, why is the core peak binding energy greater in lithium than in hydrogen? Lithium has a higher nuclear charge, so higher Coulombic attractions. Okay, so there's a little summary for you. And a final comparison of the 3 PES spectra for the first 3 elements.